Welcome to the deep dive. Today we are focusing our attention on OmniWorld. It's a really massive new data resource designed to, well, push the boundaries of 4D world modeling and AI.
That's right. And when we talk about 4D world modeling, what we mean is systems that need to understand both the 3D structure of the world's spatial geometry and how things move over time. Temporal dynamics.
Okay, so geometry and movement together.
And our mission here is to kind of unpack why a data set this big was needed, how its design tackles some key gaps in AI training right now.
And what it tells us about the current state-of-the-art models.
Yeah, what the benchmarks show about where things stand.
So the need for OmniWorld, it really boils down to a fundamental constraint, doesn't it? Like, can the data we had actually train these models to remember things for more than, say, a couple of seconds?
That's a perfect way to put it. The existing data sets, they just lack the right mix. You need complex dynamics, diversity across different types of scenes, multi-domain diversity, and really high-quality annotations.
Things like depth maps and camera positions.
Dense depth maps, accurate camera poses. If you look at benchmarks people use a lot, like Cintel, the video clips are just... well, they average only about 50 frames.
50 frames, that's barely 2 seconds of video.
It's crippling. You simply can't evaluate how robust a model is over the long term, or check its temporal consistency if the longest thing it ever sees is that short.
Okay, so OmniWorld is aiming to fix that short-term memory issue. And the core of it is this new synthetic part, OmniWorld-Game. The scale here seems like the first big headline.
Though the scale is transformative. It's a synthetic video data set, sure, but we're talking over 96,000 clips, more than 18 million frames.
18 million, how much video time is that?
That adds up to over 214 hours of continuous content. It just dwarfs previous synthetic efforts, like Flying Things plus Tray.
And it's not just the sheer amount of video, right? It's the information packed with each frame.
Right. OmniWorld-Game gives you the whole suite you need for world modeling. You get the standard RGB images, obviously, but also dense ground truth depth maps.
Ground truth, so highly accurate.
Very accurate. Plus camera poses, text captions describing what's happening, optical flow showing motion, and even foreground masks to separate moving objects.
That richness across modalities feels crucial. The model needs all those signals.
It does. It has to learn how all these things relate to each other over time.
Now, you mentioned synthetic data provides that precision, but the real world is messy, chaotic. How did they blend that sort of synthetic perfection with the diversity needed for a truly robust model?
That's where the multi-domain approach comes in. They integrated data from 4 really distinct areas to try and mirror that real-world complexity.
Okay, what are the 4?
So first, you've got the simulator domain that's OmniWorld-Game itself with its high-precision, consistent data. Second is the robot domain.
So robot interactions.
Yeah, data sets focusing on manipulation, robot interactions, think Agibot, Droid, stuff like that. Third, and this is a big one, the human domain.
Capturing people doing things.
Exactly. Diverse human activities, from inside-out egocentric views and outside-in exocentric perspectives. Sources like Epic Kitchens, HOI4D are in there.
And you mentioned it's a big part. Apparently, the human domain data makes up the largest share of the whole OmniWorld collection.
That's a really key detail, yeah. It helps ground all the geometric and temporal learning and things relevant to, well, us, human activities.
Makes sense. And the 4th domain?
The 4th is the internet domain. This pulls in more in-the-wild scene data, like City Walk. It mostly adds real-world context and extra camera pose annotations, particularly for the 3D geometry side of things.
Okay, building something this big and varied, the quality control must be intense. The annotation pipeline sounds critical. How did they ensure accuracy for something notoriously tricky like depth perception?
They had to tailor the approach. For OmniWorld-Game, the synthetic part, it's relatively straightforward. You could basically just grab the perfect depth data during the rendering process. They use tools like Reshade for that.
Direct access.
But for the public datasets, the real-world stuff, that often comes with noisy or sparse depth information. So there, they used more advanced methods like prior depth anything to essentially clean up, optimize, and generate much denser, more reliable depth maps, filling in the gaps, fixing errors.
And what about adding meaning? The text captions and motion data.
For the text, they use powerful large vision language models of something called Qwen2VL72B Instruct to generate descriptions. And these aren't just simple labels.
No,
the captions are really dense. They average between 150 and 250 tokens per description. That's a lot of detail, way more than you often see in video text data sets. offers deep context.
And tracking the motion, optical flow.
For optical flow, they picked a method called DP flow. The key thing there is it can work directly on the original high-resolution video. No need to downsample, which can lose detail.
The technical choices seem very deliberate, but I thought the way they handled camera pose estimation was particularly clever. Getting accurate camera movement in really dynamic scenes is hard.
It's a huge challenge. If the camera jerks suddenly, or if large parts of the scene don't have much texture for tracking, traditional methods just fail.
So what was their solution?
They came up with this smart two-stage automated pipeline. And the trick, the clever part, is that it uses pre-computed foreground masks.
So it identifies the moving objects first.
Yeah, and then it essentially ignores them for the camera tracking part. It focuses its tracking and refinement process mainly on the static background regions.
Ah, track the stable background, not the moving foreground chaos.
Right. By locking onto the stability of the backdrop, they get a much more robust, much more accurate estimate of the camera's path, even if there's tons of complex motion happening in the scene itself.
That is a neat trick. Counterintuitive, almost. Okay, so that level of data quality is one thing, but the real test is how it challenges the current top AI models, right? What happens when you benchmark them on this tough OmniWorld-Game data?
They set up two critical benchmark tasks using OmniWorld-Game. The first was 3D geometric prediction. They really wanted to push geometric consistency over those long, complex sequences up to 16 seconds.
Which is much longer than the usual benchmark.
Much longer and with more varied motion.
Yeah.
And what we saw was that models, which look great on short clips, really started to struggle.
Okay, so who came out on top, and maybe more importantly, what kind of failures did this data set expose? What does struggling look like?
All right, so in monocular depth estimation, that's inferring depth from just a single camera view, a model called Moj2 did the best quantitatively. It uses explicit motion cues, which helps.
Okay.
But in the video depth estimation task, which is arguably tougher because temporal consistency across frames is key, VGGT showed better performance overall across different metrics, and it was also faster, significantly higher FPS than most others.
But even the winners weren't perfect. What does poor geometric consistency look like over 16 seconds of complex motion?
The main failure mode is temporal instability. The predicted 3D structure, the depth map it might flicker, or objects might seem to subtly warp or jump around between frames.
Ah, so the world isn't stable.
Exactly. The model can't maintain a consistent understanding of the 3D scene over that longer duration when faced with all that dynamic activity. The takeaway is even the best current models still have real trouble with this kind of high dynamic, long sequence 3D consistency.
Okay, so geometry is one challenge. What was the second benchmark task?
The second one focused on camera control video generation. Basically, can AI generate dynamic video content that precisely follows specific instructions about how the virtual camera should move?
Like pan left slowly, then quickly zoom in on the object.
Sort of like that, yeah. Spatio-temporal instructions. The issue with existing datasets for this, like Real Estate 10K, is they often use smooth camera paths and mostly static scenes. Not very realistic.
So OmniWorld-Game threw in more abrupt movements, more dynamic scenes.
And when they tested the state-of-the-art models, one called Camstrist performed best. It was better at both following the camera instructions accurately and generating good quality video compared to others like MotionScript or CMI2V.
But even the winners showed there's room for improvement.
Oh, definitely. It confirmed the overall gap is still pretty large. All the current systems, they find it hard to do both things really well at the same time. Meaning they struggle to maintain high video generation quality, making the video look realistic and artifact-free, while also sticking precisely to the complex camera control commands. Usually one aspect suffers if you push the other too hard.
Okay, so the dataset clearly highlights current weaknesses, but here's a critical question listeners might have. If you train models on this huge synthetic dataset, do they just get good at playing the OmniWorld game? Is there a risk of overfitting to the simulation?
That's a fair question, and it's exactly what the validation experiments were designed to check. They didn't just test on OmniWorld, they fine-tuned existing models using OmniWorld data.
And then tested them elsewhere.
And then tested them on completely separate, well-established public benchmarks to see if the improvements transferred. And the results strongly suggested they do. Generalization seems solid.
Let's talk specifics. What about the geometric games? Did training on OmniWorld help models understand 3D geometry better in other contexts?
Yes. They took geometric models like DEST3R and CUT3R. These are transformer-based depth estimators, fine-tuned them on OmniWorld, and then tested them back on benchmarks like Centel, Bond, and KTI.
What?
They consistently performed better than their original versions before the OmniWorld fine-tuning. The fine-tuning significantly improved their temporal consistency and overall geometric prediction capabilities, even on those completely different datasets. The stability learned seemed to translate well.
Okay, that's compelling for geometry. What about the video generation models? Did the dynamic data help them follow camera instructions better, even outside OmniWorld?
Substantially, yes. They fine-tuned AC3D, which is a transformer model for camera-controlled video generation, after fine-tuning on OmniWorld.
It got better at following instructions.
It showed significant improvements in its ability to follow those precise camera control instructions. And importantly, this improvement was seen both on its original training benchmark, Real Estate 10K, and back on the challenging OmniWorld-Game benchmark itself.
So the complex, dynamic, annotated data in OmniWorld really did boost its controllable generation skills.
It seems so. It confirms the value of having that kind of data for training these types of models.
All right, so let's try to synthesize this. OmniWorld seems to tackle a major bottleneck, the lack of suitable data for 4D world modeling. It provides this massive, high-precision, multi-domain, multimodal resource. It immediately served as a tough new benchmark, revealing some Achilles' heels in current leading models, especially around long-term consistency.
Yeah, highlighting the challenges.
And crucially, it's already shown that training with it can significantly boost model performance on various tasks, even generalizing to other data sets.
The contribution feels pretty clear. It's providing that diverse, high-fidelity foundation that's needed to push 4D world modeling towards a more comprehensive long-term understanding of the physical world around us.
Before we wrap up, I think there's a final point worth reflecting on, which is just the sheer variety within the synthetic OmniWorld-Game part itself. It's not just one type of environment.
No, not at all.
The paper mentions the internal mix includes scenes from outdoor urban settings, natural landscapes, but also spans different historical eras. Ancient, modern, even futuristic sci-fi periods.
That's right. That richness across scene types, camera viewpoints, and even historical or stylistic contexts.
Yeah.
That's part of what makes it such a potentially powerful catalyst.
How so?
Well, it forces the AI models to learn about physics, geometry, and dynamics in a truly generalized way. It has to understand how things work, not just in, say, a modern city street, but potentially in an ancient forest or on a futuristic space station. It pushes beyond just our immediate modern experience.
A fantastic illustration that the quality, and maybe even more so the breadth of the data, really is foundational for where AI goes next. If you're interested in the future of 4D world modeling, it seems OmniWorld is going to be a key resource driving that change.
Absolutely. Well, until our next deep dive, keep exploring those boundaries.